Hi, so I'm taping this on Sunday afternoon. So tomorrow you have a test. That's April 27th. It's on Sapling. Its instructions are posted here. But I know most of you are going to watch this after the fact. So, but if you haven't, get that. All right. There is homework number 8 and 9 on Sapling and Blackboard. This is on lesson 10. This isn't due until Monday, May 4th on Sapling. Okay, so this is on integrated rate laws. But before we go do that, let's look back on lesson 9 a little bit. In lesson 9, we used the initial rates method in order to determine the differential rate law. For instance, for this reaction here, we did this in class. We can figure out that, okay, the rate looks something like this, okay? And so what I can do is I can use number 2, number 1, and do some math to try to figure out what n is, okay? Now, there is an easier way. Sometimes it works, sometimes it doesn't, but let's just go over that. So notice how, if I look at number 1 and number 2, I kept NH4 constant. And what did I do? I doubled NO2 minus. Well, what happened to my rate? My rate also doubled. So that means that in this case, N is equal to 1. Because I doubled this, and I doubled the rate. Let's look at the other, right? So in 2 and 3, I kept NO2 minus constant, but I doubled my NH4 plus. So I doubled that, and what happened to my rate? My rate went up by not a factor of 2, but a factor of 4, right? So that's because it's 2, in this case, to the second power. So that means that, let's make that a 2. That means that m, in this case, was 2. Okay? So remember, m and n, we need to find these. We can either do the long way or look for these clues based on it. This doesn't always work. On some of the other ones, it's harder to tell. Usually that happens when you're not simply doubling it, you're increasing it by 2.3 or something. Okay, so let's look. Last time what we've been talking about is differential rate laws. Differential rate laws include what are called differentials, right? Delta A over delta T, or more exactly, dA over dt, right? They link rates of a reaction to concentration. Now we're going to look and we're going to do some math to go from differential rate laws to integrated rate laws. Integrated rate laws link concentration to time. And this actually is really convenient because what it can say is, hey, 30 seconds into this reaction, how much of reactant A are you going to have, right? Kind of like on Google Maps or whatever. Hey, in 30 minutes, I'm going to be in LA, right? Or in 40 minutes, I'm going to be past LA in Ventura, right? Something like that. All right, so we will be studying integrated rate laws for 3 cases: 0, first, and second order. Now, there are other types of reactions, but we don't have to worry about those: 0, first, and second order. Okay, so in order to do this, we need to start off with differential rate laws. Now, remember what we said. Differential rate laws, if it's 0 order, that means rate equals K. Notice that in this case, there is no concentration because that concentration to 0 order equals 1. I have first order, which would be rate equals K times concentration. And then second order, which would be rate equals K A squared. Okay? This could also be rate K A times B, but in this case, we're going to just do it. Right? And so what we're going to do is we're going to integrate all 3 of these reactions and see what we get. Okay? We'll go over that in a little time. Now, there's one thing I'm going to do just to make life easier. I'm going to go ahead and let's say I have a plot of concentration versus time, right? This is a reactant. So the reactant goes away with time. Product forms. Now, at any given time, I can say right here is the concentration at time 0. I'm going to go ahead and just call this A and put a 0 here. Sometimes we call this A naught. This means the initial concentration. And then at any given time, this would be the concentration at time t. In this case, that would be around 70 seconds. For instance, right here, this is the concentration at 150 seconds. Okay, so that are integrated rate laws, right? Let's go ahead and look at some. Now, I'm going to go through the math. I'm going to go through it on the board behind me. I don't need you necessarily to know all this, right? Exactly how I got to it. But I want you to know that this isn't just coming from nowhere. This is coming from actual data, okay? And this is important because sometimes if we just say, oh, that's what it is, we just don't appreciate it and we don't realize that, okay, there's some meaning behind it. Okay, so I'm going to go through integration. All right, so let's say we have this reaction, A going to B, right? And we tell you that it's 0 order, okay? That means that the rate, which is equal to negative dA dt, right? It's negative because A is a reactant, okay, which means this would be decreasing, so we need that negative to make it positive. This equals K. A to the 0, but because A to the 0 is just 1, we call that K. All right, so what I'm going to do is I'm going to rearrange this. So I'm going to rearrange this to be dA equals negative K dt. And now I'm going to go ahead and I'm going to integrate it. Now, for those of you that haven't covered this in math class or not, integration is basically taking this and saying what happens over a certain amount of time, right? A differential, right? This is a speed. Integrating is saying, hey, if I go 60 miles from here to Bakersfield, how much distance have I traveled in that time, right? So if I go 60 miles per hour for the next 30 minutes, my distance is going to be different than if I go 60 miles for the next 90 minutes. Okay, all right, so dA equals negative K dt, so I'm going to integrate both. And I'm going to integrate from the time of 0 seconds all the way to some time, we'll just call that t. Okay? I'm going to do the same thing over here. I'm going to bring out this negative k because that is, I bring out this negative k because it's a constant, so I don't need to include it in the integration. All right, so what this is going to give me is, this is going to give me the concentration, right? The integral of, 1 dA would just be the concentration, and this would just give me negative k and t from t to 0. Okay? What this means is this is concentration at time t minus the concentration at time naught equals negative k t minus k times 0. Okay? This term obviously goes away, right? Because there's a 0. Okay, so this gives me A at time t minus A naught equals negative kt. I can rearrange this such that I get A at time t, that's the concentration at time t, is equal to negative kt plus my initial concentration. Okay? So this is going to be what we call the integrated rate law. So this is the differential differential rate law. This is the integrated rate law. Notice the difference. Differential rate laws, okay, actually, sorry, this is the differential rate law. Differential rate laws relate the rate to some constant and in some cases concentration, whereas integrated rate laws, they have concentration in time, right? All right, so let's look at this on the screen. Okay, so I have a at some time t equals negative kt plus a naught. Now, the reason why I like putting it like this is remember that y equals mx plus b. This is the equation of a line. So I can look at this and say, if I plot as my x-axis time, and on the y-axis I plot my concentration, okay, I can look at it. And what I'm going to get is I'm going to get a straight line, right? I'm going to get something like this, where notice how, right, I have concentration versus time. My b, that's my y-intercept, is going to be my initial concentration, and my slope is going to be equal to negative k. This is m. Okay. All right, so a zero-order reaction, the concentration will decrease over time, and it'll decrease at a constant rate. Notice the slope is constant through this whole time. Okay? Typically, this happens. This is kind of rare. This really only happens when we have something like a catalyst that removes it. Okay, one thing to remember is if I go forward in time, notice that this slope will eventually hit 0. Well, what happens once it hits 0? Well, once it hits 0, what's going to happen is it's just going to go to 0. Right? Because I can't have stuff down here because these would be negative concentrations. Negative concentrations aren't possible, right? In the same way that my bank account, once I have $0, I can't go into negative dollars. Now, in reality, I can owe money, right? But I can't literally physically have $0 or negative $2. Okay, so this is zero order. Now let's do the same thing, but for first order. Okay, now a first order reaction, well, my differential reaction is going to be different. Right? So that's, okay, so we're going to look at first order reaction. That looks like this. And we're going to try to integrate this. Okay, so this is the first order. This is differential rate law. Okay, it has dA and dt, that's differential. Okay, so I'm going to rearrange this. I need to have all my like terms on the same side. So I'm going to divide by A. I'm going to move this negative sign over there. I can just do that, right? I'm basically just multiplying both sides by -1. That'll get rid of this one, make this negative. Okay, now I'm going to integrate this from 0 to time t. Okay, now let's do the right-hand side. The right-hand side's easy. It just is negative kt from 0 to time t. On the right-hand side, the integral of 1 over a is ln a. So this, is it going to give me ln of a times 0 and time t? Okay. Integrals, it's what you learn in calculus class. It's very important because it allows us to do this. Okay. So now I have ln a at time t minus ln a naught equals negative kt minus k 0, because at time 0, t is equal to 0. But this one's not 0 because at time 0, the concentration isn't 0. Okay, so now I can rearrange this, and I can get this. ln of the concentration at time t equals negative kt plus ln times the initial concentration. Okay? And I like this again because this is similar to y equals mx plus b. Okay? All right, so let's look at this on the screen. So I have this. So what I can do is I can use this, and I can plot the ln of the concentration versus t for time. And here, I'll get another straight line where the the y-intercept equals ln a, and my slope equals negative k. Notice this is different than what we saw with the zero order. With the zero order, I could plot here, for zero order, I plotted just concentration versus time. For first order, I have to plot ln a versus time. Okay? All right. If I were to, instead of plotting ln of the concentration versus time, if I just plotted concentration versus time, what I would get is not a straight line, I'd get a curve. And I would actually get something that follows this equation here. A equals A naught e to the negative kt, where A naught is the initial concentration, K is the rate constant, T is time. This is called exponential decay. Okay, and this is actually what we see in nuclear decay, and we also see this when we're talking about viruses decaying, etc. Right? We get an exponential decay. We don't get a linear decay where it just goes straight, right? So notice how, hey, this never actually reaches 0, right? It'll just keep on going forever. All right, so that is first order. So first order, it's ln. Zero order, it's just a. All right, now let's do second order. Okay, so for second order, I have the same reaction, but now, seeing that it's second order, it's now rate equals negative dA dt equals Ka squared. Okay? Now I can rearrange this, and I can get dA over A squared equals negative K dt. All right, now I integrate both of these from time 0 to time t. And once I integrate it, on the right-hand side, I'm going to get my negative kt the same way I've gotten it the last time, because the right sides look the same for the last two. But on the right-hand side, the integral of 1 over x squared is equal to 1 over x, but it's minus. Okay? All right, so seeing in this case x is equal to a, this is going to get us negative 1 over concentration at time 0 and times t. Okay? So what that's going to do is that's going to give me negative 1 over a at time t minus negative 1 over a naught equals negative kt. I'm going to rearrange this and say, so I'm going to rearrange this and just say that I'm going to go negative 1 over at equals negative kt minus 1 over a naught. Notice this minus and minus, these become plus. So when I move that over, that's that negative. Everything's negative, so I'm just going to make everything positive. Okay? So now I have this is my integrated rate law. Okay? 1 over the concentration at time t equals kt plus 1 over a naught. Okay? Again, this looks like y equals mx plus b. So if I plot on my y-axis 1 over a, and on my x-axis time, I'm going to get another straight line where my y-intercept is now 1 over a naught. But notice my slope is just equal to k. So notice how originally in the other two it was negative. Now it's a positive slope. Okay, so a versus t, if I, instead of 1 over a, if I had plotted just concentration over time, I would get a decay like this as well. Okay, so that's 0, first, and second order. This is, right, a summary of that. So 0 order, we have this differential rate law. First order, we have this one. Second order, we have this one. Okay. These are my 3 integrated rate laws. And the reason that we do this is we can plot, or that we have them like this, is we can plot concentration versus time, and if it's 0 order, we'll get a straight line. If we plot ln versus time, and we get a straight line, that it means it's first order. And if I plot 1 over a versus time, that means it's second order. Okay? And this is actually a good method to graphically determine whether something is 0, first, or second order. All right, let's take a look at that. All right, let's say we have this. We're to determine the rate law given some data for this reaction. 2C4H6 goes to C8H12. Right? So I have some data here. At time 0, we had 2 molar. At time 5, we had 0.952. At 10 seconds, we had 0.625, etc. Okay? What I can do is I can use my calculator and I can find the ln of 2. Make sure you know how to do this on your calculator because you're going to have to do this on problems, right? So on my calculator, I would go 2, and then I would press this ln button, and that's going to give me my value, okay? 0.693. Okay. I can do the same thing with 0.952. I can take the ln of that, and I get my answer, negative 0.0492. Okay. I can do the same thing with 1 over those concentrations. So 1 over 2 gets me 0.5. Right? So here's all that data. And then what I'm going to do is I'm going to plot this versus time. If this gives me a straight line, that means it's 0 order. Then I'm going to plot this one. Oops, I meant to change the color. Give me 1 second. Then I'm going to plot this one versus time. And if that gives me a straight line, that means it's first order. And then I'm going to go ahead and I'm going to plot this one versus time. And if that gives me a straight order line, that means it's second order. Okay? Let's actually do this on the next slide. Okay? So I'm going to start off by taking my concentrations versus time. So at time 0, I have 2. At 5 seconds, I have 0.952. At 10 seconds, I have 0.625. At 15 seconds, I have 0.465. And at 20 seconds, I have 0.37. Okay? Now, I can use Excel, but even without that, I kind of look and I can kind of see that that doesn't quite look like a straight line, right? A straight line would be something like that, right? Okay, let's do the first order. Okay, so if I plot 0.693, that's right about here. Then at 5, it's 0.0492. Notice when you do the natural log of concentrations, you can get negative values. That's fine. Then this, then this, then 0.994. Again, that doesn't quite look like a straight line. You know, because a straight line would look something like that. Right? Straight line here would look something like that. I'm going to use these in Excel in a second. Okay, let's do this for second order. Take my 1 over A data. At time 0, I have 0.5, around there. At 5 seconds, I have 1.05, right around there. At 10 seconds, I have 1.6, there. At 15 seconds, I have 2.15, right around there. And then at 20 seconds, I have 2.70. Oh, this kind of looks like a straight line. Let's go ahead and put it in Excel and make sure it is, but it looks fairly straight. And I'm not perfect with this, but it looks fairly straight. Here we can see that zero order, not a straight line. First order, not a straight line, but this is a straight line, right? So that means that this reaction is second order, okay? And these values right here tell me something, okay? So I got nonlinear, nonlinear, linear, so that means it's second order. Now, seeing that it's second order, I can go ahead and I can figure out its integrated rate law, okay? And so that means that my initial concentration is, so 1 over my initial concentration equals 0.4996. So that means that initial concentration is 1 over this, so it's 2 molar. That kind of makes sense because we already started with that. And it means that this value right here, this 0.1101, that's my value for K, my rate constant. Okay? If I go ahead and then say, well, now that I know it's second order, that means its differential rate law must be this, right? Where I have rate equals negative K times the concentration squared, okay? And here I have my K value. I can figure out the units here in the same way we've done in the past based on the units of rate and of concentration. Okay, let's go ahead and have you guys do a problem. This is video problem 10A. So we did some experiments, we got some data, and that data gave us these 3 plots. And from these plots, we should be able to figure out the rate order of the reaction, the value for K, and then the initial concentration. Okay? All right, there's also some problems on worksheet number 10, 2, and 3. Being able to use graphical interpretation is very, very nice, right? We've already used the initial rates method in lesson 9. Now integrated rate laws also tell us how to do it, right? Okay, here are those 3 integrated rate laws. You should know these. Notice the difference, right? Negative, negative, positive. And then here I have, for zero order, I just have the concentration. For first, it's ln. For second, it's 1 over. All right, now, we can also use the integrated rate law to find the concentration at any time in a reaction. Okay, this is very important because this is what we want. We want to know, hey, how much longer, in 10 seconds, in 10 minutes, how much of this compound am I going to have? Okay. All right, so let's do this. So we're going to do this for 0, first, and second order. Being told that my initial A, this is A naught, is 12 molar. Remember, this 0 just means at time equals 0. Okay? And we want to use that, these three to figure out the concentration in 240 seconds. And we're told that K is equal to 0.01. Okay, so how we do this depends on the order. So we're going to go through each in turn, and we're going to get different values. Okay? All right, so let's start off with 0 order. In 0 order, concentration decreases with time. Okay? And so we're told that A at any given time is equal to negative K times T plus the concentration initially. Okay, so we're told that K here is 0.011. We want to do it at 240 seconds. Notice we're not given necessarily the units for this, but in order for it to work out, and we went through this, this has to be in molar per second times 240 seconds plus my initial concentration, which is 12 molar. This ends up getting me 2.64, so negative 2.64 molar plus 12 molar. That's going to get me 9.36 molar. Okay, so, actually, seeing that I start off with 2 sig figs, my answer should have 2 sig figs. So 9.4 molar is my answer. Okay, all right, notice that this concentration, which is my value at 240 seconds, is less than what I started with. That's good. Okay. There is one trick, and you're going to see this on the video problem. If I were to do this long enough, I might get a negative value, right? I might get negative 9.4 molar. Now, what I need to realize is that I can't get negative concentrations. And so if I get a negative concentration, that means the value is 0. Okay? An example of this is, let's say I have 3 pens, and every second I'm going to take away a pen, right? So after 1 second I have 2, 2 seconds I have 3, or I have 1, 3 seconds I have none left. Now, if I were to start off, and I'd say I start off with 3, and I take away 1 every second, if I do the math, after 10 seconds I may say, well, you'll have negative 7 pens. But there's no such thing as negative 7 pens. So I need to use my concept of concentration can't be negative. All right, so let's do this same one, but with now first order. So this is 0 order. Okay, in 0 order now, it's ln of A at time t equals negative kt plus ln of A naught. Okay, this will be negative 0.011. The units for a first order rate constants are second to the minus 1. So I'm going to multiply by 240 seconds and then add in ln of 12 molar. Okay? All right. So this ends up getting me 2.64. Remember that negative, that's going to be important. Plus ln of 12 I take 12, I hit the ln key, and I get my answer, 2.48. Okay? So when I subtract these off, I get negative 0.155. And now here's the key. Notice that this is not my answer. Okay? This is the ln of the concentration, not the concentration itself. So if I want to get the concentration at times t, I have to do the opposite of the natural log. Okay? Now the opposite of the natural log on your calculator, it's this right here. It's taking e to that value. Okay? So I'm going to go ahead and take e to this negative 0.15. On my calculator, what I would do is I would plug in 0.155, make that negative, and then I go second e to the x, and I get my value at 0.86. Okay? More. Okay? Notice, zero order versus first order, I get different values over after the same amount of time, right? These are both after 240 seconds. At zero order, I get a different concentration than first order. Okay? If this step doesn't make sense to you, go back to your math, find some videos to figure that out. If you need help, let me know. I'll try to find some for you. But this was covered in math class. Okay. All right. So, and trust me, because I hear it all the time, we didn't cover logs in math class. Yes, you did, right? It was just a long time ago, right? It was a long time ago for me too, but we need to be able to go back and figure that out when we are missing stuff. Okay, so we did zero order and first order. Zero order, we said after 240 seconds, we got 9.4 molar. At first order, after 240 seconds, we have 0.86 molar. How about second order? Okay, so second order, we have 1 over A at time t equals kt plus 1 over A naught. Okay, so let's go ahead and rearrange this. Okay? So, or actually, let's fill stuff in. So we know K, we're told it's 0.011. Now, the units for K, if it's second order, will be molar to the -1, seconds to the -1. We covered this last time when we were talking, or actually 2 times ago, when we were talking about rate laws. A second order will always have this units, okay, times 240 seconds, plus 1 over, my initial is 12 molar. Okay. So this calculation right here, 0.011 times 240 equals 2.64. Seconds cancel out. This will get me molar to -1 plus 1 over 12. This gives me 0.083. .723. That is 1 over AT. So if you have AT, right, I'm going to do the opposite of this. And that's going to get me my concentration. Okay, so zero order, I get a different concentration after 240 seconds. Okay, here is, I went the wrong way. Here is the sum of those calculations, right? Notice in each one we use a different equation based on whether it's zero, first, or second order. and I get different concentrations after that 240 seconds. Notice when we do first and second order, I need to go ahead and calculate my final concentration. I can't just do this initial step like I can with the zero order. I need to convert to my actual concentration. Okay, so you're going to do your own problem. This one I am, yes, that's right. This looks the same, but notice that this is now with a different K value, right? So we're going to do the same problem, 12 molar, 240 seconds, but now my K value is different, right? Previously, it was 0.011. Here it's 0.11. Okay, so do that. We'll go over this again in class or in the other video, and then we'll do it. And then we'll move on. Okay, so we have one last problem we're going to do. And this is a problem that is just phrased a different way, but it's good to know how to do this. All right, so let's say we have this reaction, A goes to B. We're told it's first order, so that means we're going to use this equation. And we're told that here's my K, and we're asked how long will it take for 5% to decay? Okay? The reason why we're asked about this for first order is because the first order, this is exponential decay. And exponential decay is what we have when we have nuclear decay, right? Nuclear waste. Right? So what we want to know is, hey, I have this nuclear waste. How long is it going to decay before it's good? All right, so let's look at this. We're told that, or we're told it's first order, so that means that ln of A, the time t equals negative kt plus ln A naught. Okay, we're told that we want to know how long will it take for 5% to decay. So notice this one's different. In the past, we've been given a time. Here, we're asked for that time. Okay, so we want to know the t. All right, so let's plug in what we do know. We know the value for k. We don't know the value for t. That's what we're trying to find out. And we have our ln AT and ln A naught. Okay, but it doesn't tell us anything else. But notice how it tells us that 5% decay. What does 5% decay? Well, 5% decay is the same as if I say, hey, I had $100 and I spent 5% of it. Now I have $95. Right? So 5% decay means I have 95% remains. So what that means is that if I initially had A naught, my value at time t, the time I care about, is going to be 95% of this, or 0.95 times A naught. Okay? So now I can plug this in for my ln, or for my AT. And now I can go ahead and I can try to figure this out. Okay, so let's go ahead and do this. So when I rearrange this, okay, I'm going to get ln 0.95 A naught minus ln A naught equals negative 0.011 times t. Okay? All right. I can rearrange this, and I can use the fact that when I'm dealing with ln's, if I have ln of one thing minus ln of another, this is the same as ln of 0.95 A naught over A naught. My initial concentration, negative 0.011. Right? This is a rule for LNs, right? Natural logs. And if you don't remember what a natural log is, go back and study it, right? Figure out what it means. Figure out what log means. Figure out what ln means. And figure out why this is the case. Okay, so these cancel out. This is ln 0.95 equals negative 0.011 t. Right? The ln of 0.95 is negative 0.051 equals negative 0.011 t. So t is 4.6, and the t has to be, in this case, in seconds. All right, so that is it. Here it is on the screen, right? Or actually, on the screen, I got 4.7 seconds. I rounded at 1 point, but I get the same answer. All right, so lesson 10, we talked about integrated rate laws, right? Integrated rate laws can be used for two things, right? We can use them to determine the rate law, right? If I do A versus T, that'll be zero order if it gives me a straight line. ln A versus T will give me a straight line for first order, and then 1 over A versus T will get me it for second, okay? Then we can use these rate laws to determine concentration at any time, time to reach a given A, that's what we just did, and then half-life. This is something we'll do in lesson number 11. Okay? All right, so that is it for lesson 10. Actually, I'm just remembering one thing, so let me go back in time a little bit to video problem 10a. Okay? Now, this one asks for the value for k, and so you're going to find this based on the rate order. Notice one thing. Time here is not in seconds, it's in minutes. So that means on a lot of the calculations we've been using it and we're saying per second, right? Here it's going to be per minute. So include that. Okay. All right. So that is it for lesson 10. Reminder that lesson 10, the homework for that is due Monday, May 4th via Sapling. But before that, between now and the time that's due, you have your test number 1. So I wish you good luck on that. If you already took it, I hope it went well. And I'll talk to you later. All right.